Welcome back. In this video, we will learn the parameter estimation. This will make our models perfect and makes the error very small. Let's get a quick start. When we train a models, there are two types of parameters. The one can be obtained from the learning. It will be changing by process of training the models. And the other, we can't obtain from the data, but it set based on the human's experience. That is called hyperparameters. A parameter is the part of the model that is learned from the history training data and key to the machine learning algorithms. It has the following features. It requires by the model when making predictions. Its values defines the skills of models on your problems. It is the estimator as all learned from data. It is often not set manually by the practitioners. It is often saved as a part of the learned models. For example, and the weight and the bias in our models, and in support model there are the support vectors machine and the support vectors and coefficient in linear regressions or logistifications, and they are the parameters. And for hyperparameters, it has the following features. It is often used in process to hyperestimate models parameters. It is often specified by the practitioners, and it can often be set using the heuristics. It is often trained for a given predictive modeling problems. For example, learning rate for training neural networks, and numbers, iterations, and bench size, action functions. They are also the hyperparameters. And since hyperparameters is set based on human's experience, how we set them by our experience, here are products for searching for hyperparameters. And we should divide the dataset into the training set, verification set, and test set. Optimize the model parameters in the training set based on the performance in the indicators of the models. Search for the model hyperparameters in training set based on the performance indicators of the model. And the step 2 or step 3 are performed alternatively. And finally, open the parameters and hyperparameters of the model and assess the model in the test set. There are 4 common search algorithms for hyperparameters: graded search, random search, and graded search and random search is cost a lot of times. We usually use the Bayes search and intelligent search. Also use the line regression to predict the parameters. As I told you before, a dataset can be split into the training data and test data. How to split? And let's see some details. When the dataset is too small, alternatives the process enable one to use the all examples to estimations of meaning test error at the price of the increase in the computing cost. So we introduced the concept of the cross validation. It is the statistical analysis method to use to validate the performance of the classification. The basic idea is to divide the original data set into 2 parts, training set and validation set, and train the classification on training set and test the model on the validation set. Then obey the performance indicators of the classification. For key-fold cross-validations and partition the original training data set into key values sublet. For example, if it's a data set, we can split into the key value. If the key is equal to 5, we can split the data set into the 1, 2, 3, for these five parts, and each part will serve as the test. Maybe we can use the test data, and test set, and we can use the first part as the test set and at the first time, and then the second time we can use the second data, use the test set, and then use the third times, maybe use third times to use the third data as the test set. That will cause the key cross validation, and each smaller data set will be served as the test data to test our models. With the first data set as the test data, the other data set as the training and the training data set training our models. That's the idea of the k-fold cross validation. And we know hyperparameters is set by human, and how the model set parameters. Let's see the series of the parameter estimation. Here is the definition of the parameter estimation. Suppose that there is a static population, and its distribution function is x, and where theta is unknown parameter. Now we samples the population and obtain the samples x1, x2, x3, xn, and we need to find the estimator theta of the parameter theta, or estimator theta's function, and g theta. So this problem is called a parameter estimation, encoding the parameter in encoding point estimation and internal estimation. Suppose u is equal to 7, and this is a point estimator. If the u within is the 5.12, and this is the interval estimation. And the right is the point of the estimation in the statistical method. The statistical method we can split the method into the describe statistic and the statistical inverse, and the parameter estimation will belong to the statistical inference. And here is the example of the point estimator. Here is the definition of the parameter estimation. Suppose that there is the statistical population, and its distribution function is x, mean value, and its sigma prescribed, and the randomly select the 100 best and obtain their weight data, and it's 10, 7, 5, 6, 6, 5, 2. Now we have the 100 fingers, and how do we estimate their mean value and variance value? So for a point estimator, we need to construct a function of the appropriate samples, and x1, x2, and is the x1. Once we have the sample, we can input the value into the function and obey the values, and that can be used to estimator of the use, and then the testers, this series of samples is the parameter of the pointer estimators. So the problem appears, which estimator can be used to estimation new, the meaning. How do we accept the estimators? We can use the mean of the samples, median of samples, and other statistics method. And the statistics assessment standard is unbiased. It is the important characters of statistics assessment standards. And the unbiased is the character like that. The biased is equal to the expector minus our estimator, and the estimator is to be asked if the bias is equal to 0, An estimator theta hat is said to be asymptotically unbiased if the limit bias is equal to 0, and it also can asymptotically unbiased. And for example, suppose this list of samples and the sample from the population X, and its expector is equal to the mu's, and its device is equal to the sigma squared, and prove that if the X hat is the mean of the sample's values, and its unbiased estimator is the mu. Also, we want to prove and the sigma hat is the unbiased estimator of the variance. And the second standard is valid for the x1, x2, and x3 is a sample of the population X, and the following standards are biased estimator of the mean values. Which one is the optimal? So we can calculate use the mu 1 hat, mu 2 hat, and mu 3 hat, mu 4 hat. Which one is the optimal? So let's suppose that theta hat and theta 2 are two unbiased estimation of the theta, and if the device of theta 1 hat is smaller than device of theta 2 hat, so we can see that theta 1 hat is more valid than theta 2 hat. So we can prove like that is to prove that process. We don't talk more about that. So we can the valid which unbiased estimator and the mean u is the optimal. We will see their device. So first we compare their unbiased, and then we compare their device and see their valid. Let's see the last standard, constant. The constant used the probability to calculate the probability of the difference between the estimator and the values, and it will is larger as the error, and then to calculate the probability is equal to 0. If it's very close to 0, it will be too constant. That is how to judge the estimator is the standard is the used constant. Let's see more useful method to estimate the parameter, and what's the maximum likelihood estimation. Suppose that N contains the number of the black balls and the number of white balls. However, it's not known whether the N's have more black balls or more white balls. I don't know that. And if the sampling is performed for n times, and the probability of the n numbers balls as that, we can calculate it. And where Q is equal to the 1 minus the P. According to the assumption, we will know the P is equal to 1/5 or 3/5. If n the times n is equal to 3, the x probability under this one. If the probability is equal to the 3/5, and we have the x will equal to 0, it will have the probabilities, and if the x is equal to 1, it will be calculated that the p x will equal to is the 9/64. So when the probability is equal to 3/4, we will calculate this probability. And when the probability is the 1/4, we calculate this probability. So we will know that when the x is equal to 0 and 1, we will choose the search the large number list with when the probability is the 1/4, the probability will be large, and when x is equal to and or 3, we will choose the ability is equal to 3 percent fifths, and it also is large, so that will calculate the expression is very large. So we will choose when it's x equal to different numbers, we will choose the larger the probabilities, and that's the maximum likelihood estimation core ideas. Let's take another example. If the students went out hunting with a hunter, and a hare ran into from in front of them, and one shot was fired, and the hare fell down. Do you think who shot the hare? You might think that chance of the hunter hit the hare, because we know the hunters may have the larger probabilities than the students. So that's the basic idea of the maximum likelihood estimation, because we all know the hunters have the larger probability to shot the hare, and we will choose the larger probabilities and to make the things occur. And here we learned about maximum likelihood estimation principles, and this about suppose the samples from the population X, and it's the joint descent, and we will like this. We will define the likely function. It's the function, and the X is the observed values, and the L state. This function is a parameter state, can be used to assess the probability state. So we will choose where theta is the very large to make the function very large. Maximum likelihood estimation used the theta hat to minimize the landing. As I told you before, we will choose the theta, and this theta can make this function large when the function is very large, and it will find the best theta. So that's the maximum likelihood estimation. Let's see the purpose and how to calculate it. This likelihood function we will sort of design it like that, and then we will to log down, because we want to make the functions is easy to calculate, and divide the function with respect to p. We will calculate its derivative and equal to 0. Then we will finally we get the p hat is equal to the x hat. So that's how to calculate the estimator using the max likelihood estimators method. And let's see the Biased method. The Biased estimation is also a probability-based method, and Biased theorem, and like we talked about that the conditioning formulas, and to calculate the posterior and probability, and then we will use the probability to make these probabilities and two very large, and we will get the largest one, and we will get the estimator is which estimator is best. After we learned the parameter estimation, we know how to make our models perform better. But when the features are too large for local constraints and smooth regularizations and meaningful learnings, machine learning often failed to do that. So it is challenging for traditional machine learnings that motivates the development of the deep learnings. In next video, we will introduce the deep learning part, and I hope to see you in the next video. Bye.